figuring out tension problems is just basically figuring out your total forces and everything that's acting on any particular object that's involved. So you kind of have to look at it in a free body diagram kind of way. The way that I would look at something like this is the first thing I'm going to do is simplify the situation. I'm going to look at one of the masses and kind of go from there, because this string is just the same string, so there's only one tension here, right? So I'm going to pick the focus on the mass that's driving the system. So obviously, if I've got gravity working on this side and gravity working on this side, this guy's going to win, right? I actually had a teacher who, instead of drawing weights, he would draw a monkey on this side, and this is the skinny monkey. And he's holding onto the rope here. And on this side, just to kind of give you an idea of sort of a physical context, that's the fat monkey, right? So the fat monkey is going to make the skinny monkey go up. So if this guy weighs 1 kilogram and this guy weighs 2 kilograms, then the force of gravity on this guy is going to be 10 newtons. The force of gravity on this guy is going to be 20 newtons, because they're using 10 instead of 9.8. So that means that my net force, which is always what I'm interested in, is going to be 20 minus 10, because they're acting in opposite directions, and the net force is going to be 10 newtons. So I want the acceleration on the system. It's going to be equal to my net force over my total mass, and in that case, my net force being 10 newtons, total mass is 3. That's going to give me an acceleration of 3.3 meters per second squared. To me, this makes more sense than the way that you showed me in the book, because they're just manipulating formulas. And if you get to the test and you're looking at it going, oh, how did I use those formulas again? If you don't have a logical context for it, then sometimes that slips your mind. Anyway, so this is my logical context. The net force has to be the 10 newtons that is being used to actually move the rope. So there's your 10 newtons. And that's going to be affected by the mass of the system, which equals 3 kilograms, because this guy's 1 kilogram and that's 2 kilograms. Makes sense that the mass of this little guy is going to slow down the system accelerating. So we use those numbers together, we get our acceleration of 3.3 meters per second squared. Now we look at the tension part on this rope. So tension is the same for both, so let's focus on what's happening on this side. Now, this guy's going down, which is actually relieving some of the pressure that's been caused by gravity. If this system was stationary, then the 20 newtons would be pulling on the rope, but some of it's been relieved, so it's only like the 10 newton force that's going. So I've got this 3.3 meters per second squared, and tension is mass times acceleration. However, we've already got acceleration due to gravity, right? If he was just free falling, he'd be going at 9.8, or in this case 10 meters per second squared, straight down. But he's not free falling. He's being held back. He's not being held back completely. So what happens is the tension that's left in the rope is the tension caused by the difference between if he was free falling, which would be no tension, and what he has going on with this acceleration. So I'm going to make a new formula where it's his mass times the difference between the acceleration of gravity, which would be free fall, and the acceleration that's actually here. So basically, the number here is going to be smaller because the tension is being relieved in the direction of gravity. I don't know if that makes sense, but I'm going to go, his mass is 2 kilograms, and, sorry, not 9.8 in this case, it's 10 minus 3.3. So I use my calculator, and it tells me that it's 2 times 10 minus 3.3 is 6.7, so about 13.4 newtons. and your book has 13 newtons because they rounded off, because they're using significant digits. If I had used this monkey, which I could do to figure out tension, then I would go tension equals mass times acceleration, which in this case, though, he is trying to go down at 9.8 or 10 meters per second squared, but he's failing. He's going the other way. So the tension in the rope is actually going to be G plus A, or you could say G minus negative A because it's going the opposite direction. So the tension for this guy would be 1 times 10 plus 3.3, which is going to give you 10 plus 3.3 is just 13.3 newtons. So given room for significant digits, this number is the same as this number. So it doesn't matter which of the bodies you pick to calculate your tension from. You just have to remember that if the motion is going in that direction, then it's going to be relieving the tension of gravity, so you subtract. Or if it's going against it, then you would have to add them because it's actually increasing the tension. Normally, I just pick the big one. Like I said before, I pick the one that's causing the motion, and I just use T equals M times G minus A. It's a lot different than the setup that you showed me. Go with whichever one makes more sense to you.